We are starting our unit on graphing rational functions. We're going to start by exploring the parent function of f of x equals 1 over x. Now, considering the function, without graphing it, how can you determine its domain? Okay, now think back to when we worked with rational functions before we went for winter break. And because we know that rational functions are fractions, we know that x cannot equal 0. So the domain is indicated by the fraction, right? So because you cannot divide, remember a fraction is division, because you cannot divide by 0, x cannot equal 0. So for the domain, now I realize we are asked to write it in 3 different notations. Remember, as an inequality, we would simply say x is less than 0 or x is greater than 0. This means we are splitting it up into 2 different sections because the only value we cannot have is 0 for x. As set notation, remember we use curly brackets. We state the domain for x, given that x cannot equal 0. And interval notation, remember, is when we use the parentheses or brackets. Now, because we are talking about left to right, right, we can include everything except for 0. We're going to start with parentheses from negative infinity up to 0, not included, so we use parentheses, joined by, or union, and then from 0 to positive infinity. So that would be the domain for this function. Now let's go ahead and graph it and explore what this graph would look like. We are given a table of values. You can see we have f of x equals 1 over x. And you are given a set of values, so I'm going to ask you to plug those into your calculator, or if you're doing this by hand, that's also fine, right? 1 divided by negative 2 is simply negative 1/2. 1 divided by negative 1 is negative 1. 1 divided by negative 1/2 is negative 2. And 1 divided by negative 0.25 gives us negative 4. Okay, now on the positive side, right, negative values is everything less than 0. Positive values would be everything greater than 0. Repeat the same process. 1 divided by 0.25 gives us 4. 1 divided by 0.5 gives us 2. 1 divided by 1 gives us 1. And 1 divided by 2 is 1/2. Now, let's go ahead and plot these points. We have negative 2, negative 1/2. Negative 1, negative 1. Negative 1/2, negative 2. And negative 0.25, negative 4. So you can see my points. And then on the other hand, we have 0.25, 4, 0.52, 1, 1, and 2, 1/2. Now you can kind of see what's happening here. As we approach 0, right, if you look at the dots, as I approach 0, they're getting closer and closer to 0, but they are not going to ever cross 0. And same thing happens on the x-axis. As you can see, it's coming down, right, and it's not touching that line. If you recall, we did work with asymptotes once before. Rational functions also have asymptotes. However, in the past, when we looked at asymptotes only existed, or only one asymptote existed. When it comes to rational functions, we have 2 asymptotes. Okay, you can see our function. Our function is 2 separate drawings on our coordinate plane, but our asymptotes in this case are located at the x and y axis, meaning our graph is going to approach these lines, but it is never going to touch or cross these lines. Okay, now we will be using the points +1, and -1, as reference points. So when we transform these functions, these are the 2 points that we're going to be focused on in terms of transformations, and using these as our guide points for when we do for when we do graph our functions. Now, determine the end behavior of f of x equals 1 over x. As x approaches infinity, f of x, you can see, is approaching 0. And as x approaches negative infinity, f of x also approaches 0. For the range, in set notation, okay, let's go ahead and look at the range. So as we come up from bottom to top, you can see that we can have any number, because we have our function here, any number except for 0. There is nothing at 0, and then it continues on past 0. So in set notation, we can say curly bracket for y is everything except for 0, right? Or y cannot equal 0. Now we could also say, depending on how you would write your inequality, we could also state it as y is less than 0 or y is greater than 0. Set notation does correlate to inequalities, and remember, it all comes back to preference. Do you want to state your two different values, or do you just want to state what value y cannot be? Okay. Now, determine the end behavior of f of x equals 1 over x near x equals 0. Okay, this means we are going to look at end behavior as we come in to 0. We are used to looking at end behavior as x approaches infinity going to the right, and then as x approaches infinity going to the left. This time we're looking at approaching 0. So as x approaches 0 from the positive direction, meaning as x approaches 0 from right to left, this would be from 0, positive end. Okay, and we write this as x approaches 0, and we use a superscript here, positive from the positive direction. Okay, f of x does what? And we can do this using a table of values. So if you take your calculator and you substitute 0.01 in for x, 1 divided by 0.01 gives us a value of 100. 1 divided by 0.001 gives us a value of 1,000. And 1 divided by 0.0001 gives us a value of 10,000. So you can see what's happening here is as we get closer and closer to 0, because remember, these numbers are getting closer and closer to 0. 0.0001 is a lot closer to 0 than 0.01. So as x approaches 0 from the positive end, our f of x values, what's happening here is they're increasing. Our values are increasing, and our y values are approaching positive infinity. If we do the same on the opposite end, as x approaches 0 from the negative end, so coming in from left to right, okay, let's take a look at this one. As x approaches 0 from the negative end, what are your f of x values doing? How are your y values behaving? Now, you can easily see from the graph that our y values are approaching negative infinity, right? Because they're getting smaller and smaller. However, let's do this using our table of values. So if we substitute 0.01, what's 1 divided by negative 0.01? We get a value of negative 100. 1 divided by negative 0.001 gives us negative 1,000. And 1 divided by negative 0.0001 gives us negative 10,000. So you can see that our values are decreasing, right? We're getting further and further away from our y-axis there. So as x approaches 0 from the negative direction, f of x approaches negative infinity. Okay. Rational functions are one type of function that has asymptotes. An asymptote is a line that a curve approaches as it heads towards infinity. Again, we have already worked with asymptotes, so we know what an asymptote is. And as we discussed earlier, the asymptotes we see on the graph of f of x equals 1 over x are located at the axes. Okay, so that means we have a vertical asymptote at x equals 0, and we have a horizontal asymptote at x equals, oops, not x, at y equals 0. Okay, how do these relate to the domain and range? Well, for the vertical asymptote, we cannot include in the domain that x value in the domain. And for the horizontal asymptote, that y value cannot be included in the range. All right, now let's go ahead and look at the graphs of 1 over x. We're going to graph using a couple of transformations here. The first one, we have f of x equals negative 1 over x. So this is what we're looking at here. When we have a negative on the outside of the fraction, that is a reflection over the x-axis. Okay, this means that our a value is negative 1. When you have a reflection across the x-axis, remember, this is our x-axis. Our parent function, this is our parent function. You can see our parent function is located in quadrants 1 and 3. Reflecting it across the x-axis would take quadrant 1 and flip it over to quadrant 4. Same thing for the second portion here. Quadrant 3 reflected over the x-axis would flip over to quadrant 2. So taking our reference points, remember our reference points were 1, 1 and negative 1, negative 1. Reflect them over the x-axis, giving us points at 1, negative 1 and negative 1, positive 1. So a reflection over the x-axis is now located in quadrants 2 and 4. Similarly, when you have a transformation where the negative is in the denominator, this is an indication that b is negative 1. And when b is negative 1, you have a reflection over the y-axis. Okay, so similarly, we had our parent function, 1 over x, is located quadrants 1 and 3. Remember, we still have reference points at 1, 1, negative 1, negative 1. But now reflecting it over the y-axis means I'm going to take 1, 1 and reflect it to quadrant 2, giving me a new point at negative 1, positive 1. Likewise, I'm going to take my reference point in quadrant 3 and reflect it over to quadrant 4, giving me a point at positive 1, negative 1. So you can see reflection over y-axis takes my graph to quadrants 2 and 4, just like a reflection over the x-axis did. Okay? Because the reflection of the graph over either axis results in the same graph, the function f of x equals 1 over x is an odd function. Before we get into the next part of transforming simple rational functions, let's go back and talk about our parent function. Remember, our parent function is f of x equals 1 over x. Now, when it comes to a transformation, we are going to use g of x equals a times 1 over b times x minus h plus k. Now, I know you guys should remember this. We have talked infinitely about what a, b, h, and k do. Remember, these are the specific transformations we have worked with every single type of function we've discussed in the past. So, what does a do? Remember, if we have a negative a, it is a reflection over the x-axis. Okay, that's one function for a. If a is less than 1, then it is a vertical compression. And if a is greater than 1, then it is a vertical stretch. B behaves very similarly to a, okay? However, it is the opposite. If we have a negative b value, then it is a reflection over the y-axis. If b is less than 1, then we have a horizontal compression. And if b is greater than 1, then we have a horizontal stretch. Now, remember that h plays the role of a vertical translation, meaning we're moving left, I'm sorry, not vertical, a horizontal translation, meaning we're moving left or right, okay? If we have a positive h, we move right. And if we have a negative h, then we move left. Okay, remember the key with h is always the opposite of what is listed. And finally, k. K plays the role of a vertical translation, meaning it's going to move up or down. So a positive k moves our function up, and a negative k moves our function down. Okay, so again, we've discussed these endlessly, right? We have discussed these several times in the past. Transformations are going to be no different. A, B, H, and K have always had the same behaviors when it comes to transformations. So we're going to apply these transformations and discuss how it's going to affect our functions. In a quadratic function, H and K gives us coordinates of the vertex. In cubic functions, h and k gives us the coordinates of the point of symmetry. Now, in a simple rational function, h and k give us the asymptotes. So it's going to be a little bit easy or a little simple for us to identify these asymptotes. Okay, because our vertical asymptote crosses the x-axis, x gives us, or x is given to us by h, and our horizontal asymptote, oops, that should say y, not x, our horizontal asymptote is located at y equals k. So let's go ahead and look at some examples here. First example tells us, tell the transformations applied to the graph of f of x equals 1 over x to produce the graph of g of x. Remember, we're comparing g of x to the parent function 1 over x and describing these transformations. Then give the equations for the asymptotes and the domain and range in set notation. So looking at A, we have 2 times 1 over x minus 3 plus 5. Remember, your first step should always be to identify your A, H, and K values. In this case, you can see that A is equal to 2, H is equal to positive 3, and K is equal to positive 5. So let's start by identifying our asymptotes. Okay, vertical asymptote is located at x equals 3. Remember, x equals h. And our horizontal asymptote is located at y equals k, which means y equals 5. Now that we've identified the asymptotes there, let's go ahead and describe the transformations. And remember, the transformations are simply based on your a, h, and k values. So because a was equal to 2 and it's positive, that means we had a vertical stretch. Because h is equal to 3 and it is positive, that means it moved right 3 values or 3 spaces. And because k is equal to 5, that tells us that it moved up 5 spaces. State the domain and range in set notation. For the domain is affected by the h value because it is telling us where your graph cannot, cross that line. So because our asymptote is located at 3, that means, in set notation, that we're going to come in from negative infinity up to positive 3 and from positive 3 to infinity because x can be any value except for 3. Same thing for the range. In this case, our horizontal asymptote is located at y equals 5. So our range goes up from negative infinity to positive 5 and from 5 to positive infinity. Okay, let's try one more. Let's go ahead and try B. For B, let's start with our transformations here. We don't have an A value, so there is no transformation for A. H is negative 4, which means that our function moved left 4 units. And K is negative 6, which means that it moved down 6 units. Okay. Our vertical asymptote is now located at x equals negative 4, and our horizontal asymptote is now located at y equals negative 6. For the domain, we go from negative infinity to negative 4, and from negative 4 to negative infinity. For the range, we're going to go from negative infinity up to negative 6, and from negative 6 to positive infinity. All right, go ahead and hit the pause button and try C and D.